So I'll be working some problems from this book by Brown and Churchill, and I'm starting with exercises following section 2. Number 1 asks us to verify some relations. Part A, we are given this equation that we need to verify. So what does it mean to verify an expression? In this case, we need to show that this side is equal to the other side. We can start out by removing parentheses from this term and then multiplying out I. We get I minus square root of I squared, continuing to then we can factor in the minus sign, so we can remove these parentheses and we'll get minus I plus square root of 2I squared. Here we have minus 2I, and then we have this term square root of 2, but here we have for the last term we have I squared, but we know that I squared is equal to minus 1, so we have minus square root of 2. So the squares of 2 cancel out and we're left with minus 2I, exactly what we wanted. So we have proved this relation. Part B asks us to show a relation that is written in coordinate form. In this case, since it's much easier to deal with the imaginary number being multiplied than the coordinate form, I will first convert it. So I'll have here 2 minus 3I, then minus 2 plus I. In this case, so then I will multiply the terms out. So I have here 2 times minus 2, I'll have minus 4, and 2 times I have 2I. Then minus 3I times minus 2, I'll get plus 6I, and then I'll have 3I squared. Simplifying this equation a bit, I group these two terms together to get 8I, and since I squared is minus 1, I'll have here plus 3. This in turn becomes minus 1, 8I, and writing it in coordinate form gives us minus 1, 8, which is exactly what we wanted. For part C, we are given an equation that's a little bit longer. I will first start out by rewriting this equation in the other form. So I'll have here 3 plus 1 plus I, then I have 3 minus I, then 1 over 5 plus I times 1 over 10. Well, this relation is gonna be, then I will multiply out the first two terms and I'll get 9 minus I squared. Here I have 1 over 5 plus I 1 over 10. Since I squared is just minus 1, I have the negative signs cancel out and I'll get 10 times 1 over 5 plus I 1 over 10. Multiplying through the 10, I get 2 plus I. And converted to the coordinate form, I get 2, 1. Precisely what we were looking for. Problem number 2 asks us to show the following relations. Here we have that real part of I times z is equal to the negative of the imaginary part of z. In this case, z is a complex number. And since it's a complex number, we can write it as z0 plus I z1, where z0 and z1 are real numbers. In this case, z0 is the real part and z1 is the imaginary part. I want to show that this side is equal to this side. So what I will do, I will plug in this equation into z, so I get real part of I z is equivalent to z0 plus I z1. Then multiplying through I get that I z0 plus I squared z1. In this case, I squared is minus 1, so I'm taking real part of minus z1 plus I z0. And the real part of this number is going to be minus z1. The other side, imaginary part of z, is just going to be imaginary part of z0 plus I z1, which is precisely z1. So we get that this is equal to minus z1. So both sides are equal to each other, so we have proved the relation. Part B asks us to show that imaginary part of I times z is equal to real part of z. So in this case, z is once again z0 plus I z1. Then imaginary part of iz is gonna be I z0 plus I z1. Multiplying it I through, I get I z0 plus I squared z1. In this case, since I squared is minus 1, I get minus z1 plus I z0. So the imaginary part will be z0 of this number. On the other side, I have real part of z. It's going to be real part of z0 plus I z1, which is just z0. So we get z0. So both sides are equal to z0. Number 3 asks us to show 1 plus c squared is equal to 1 plus 2z plus c squared. It seems quite trivial. We know that complex numbers are commutative, associative, and they follow the distributive law. So all the basic rules of arithmetic apply. And not only that, real numbers are a subset of complex numbers. So, for example, 1 can be written as 1 plus I times 0. So 1 is technically a complex number as well, with imaginary part of 0. So our rules of arithmetic that are given to us, say on page by equations 1, 2, and 3 in part 2. So then the way we can argue this is we can just simply say by equations 1 through 3 in part 2, we can just write 1 plus c squared as 1 plus c times 1 plus c. Then we can multiply everything out to get 1 plus z plus then z times 1 is z plus c squared, which is just going to be 1 plus 2z plus c squared. Number 4 asks us to verify that z equal 1 plus or minus I satisfies the equation z squared minus 2z plus 2 equal to 0. So in these kinds of problems, you just simply plug z into the equation and work out the arithmetic. So for part 1, we have z is equal 1 plus I. Plugging it in, we get 1 plus I squared minus 2, 1 plus I plus 2. In this case, this will multiply out to 1 plus 2i plus I squared. Then distributing 2 in, we get minus 2 minus 2i. and then plus 2. So first we notice that 2 cancels as minus 2, 2i cancels as minus 2i, and then we're left with 1 plus I squared, which is just minus 1, and these in turn cancel out, and we get 0. So it works. For part 2, we have z is equal to I minus 1 minus I. So plugging it in, we get 1 minus I squared minus 1 minus I plus 2. In this case, we also get that 1 minus 2i plus I squared, then multiply through 2, we get minus 2 plus 2i, then plus 2. So 2's cancel out, 2i's cancel out, and we're left with 1 plus minus 1, since I squared is minus 1, which is again 0. So this finishes this problem. Number 5 asks us to show that multiplication of complex numbers is cumulative, which is equivalent to a times b is equal to b times a. Since a and b are complex numbers, we can write them as a is equal to a naught plus I a1, and b is equal to b naught plus I b1. So in this case, we sort of just plug it in and carry on the multiplication. So we have a naught plus I a1. We want to multiply these numbers through to get a naught b naught plus I a naught b1 plus I a1 b naught plus I squared a1 b1. We know that real numbers are cumulative, so we can change the order. So I'm going to reorder it, so that's given. And this equation is going to be equivalent to b naught plus I b1 times a naught plus I a1. But this is just our b multiplied by a. And so we have shown that ab is equal to ba. And although this problem might seem silly, this is often how they want us to prove certain obvious relations, because since complex numbers are a little different from real numbers, it is not given that all of the rules of arithmetic carry over to complex numbers. In this problem, we are asked to prove that associative law holds for complex numbers. So what they want us to do is to use the fact that real numbers are associative to show associativity for complex numbers. To do that, we will break up a, b, and c into their real and imaginary parts. So we'll have a naught plus I a1 plus b naught plus I b1 plus c naught plus I c1. In this case, this is a, this is b, and this is c. But these are all our familiar real numbers that we know rules of arithmetic for, so we can rearrange the parentheses in this case. So we have here a naught plus I a1 plus b naught plus I b1 plus c naught plus I c1. So now that we have moved the parentheses, we can say that this is a, and this is b, and this is c, and we got our relation. This proves the relation. For part B, we are asked to prove the distributive law. So we have that AB plus C is equal to AB plus AC. Once again, we will write it out as in terms of A0 plus IA1 and carry through the addition and multiplications. So we have here A0 plus IA1 followed by B0 plus IB1 plus C0 plus IC1. So the trick here is not to completely multiply it out, but sort of, try to make our life easier. So here we have A0 plus IA1 times B0 plus IB1. So I'm carrying out A0 plus IA1 for this term and this term. Then I'll have A0 plus IA1 times C0 plus IC1. But this is just A and this is just B. This is just A and this is just C. And therefore we proved the distributive law. Great. Yeah. In number 7, we asked to prove the following relation. Although it seems obvious, it's just the distributive law, but for 3 terms instead of just 2. We have to use the relation that CZ1 plus Z2. This is the relation given to us in the text by equation 2-3. We know that complex numbers are associative, so we can rewrite it as Z1 plus Z2 plus Z3. And now we just have 2 terms, so we can apply the distributive law. So we have Z times C1 plus Z, Z2. So here I'll have associative. But here we have 2 terms, multiplication, just 2 terms. So I can apply the distributive law again. So I get C1 times C1 plus Z times C2 plus Z times C3. So I applied the distributive law again. So I have arrived at this equation.